Okay. Welcome to today's lesson. This section is presented by the group 35 of the IT PowerPoint groups. We are presenting on computer optimization processes. So these are some of the references that you can read about computer optimizations. So these are the lecture outlines, basic definitions, problem formulations, classical optimization, direct search, gradient methods, constraint optimization, LeBron, and constraint optimization, non-LeBron. So the aims of today's or this section to understand the principles and techniques of optimization and their application in computer science, to learn how to model and solve optimization problems using various algorithms and techniques, to analyze and evaluate the performance of different optimization techniques, to apply optimization techniques to real world problems and computer science and other fields. So when we talk about computer optimization is the process of enhancing performance of computers, its efficiency, speed of computers, system or softwares. So the computer optimization process typically includes assessment, cleaning, disk management, drive updates, malware removal. So this involves various techniques and strategies to make the system or application run more smoothly, quickly, and with fewer resources. So let's move up to a standard optimization problems or standard optimization problem. A standard optimization problem is a mathematical problem that involves finding the best solution among a set of solutions given certain constraints. The problems is typically formulated as maximum, minimum, subject to, and other functions and equations are used in computer optimization. The optimal solution to the problem is the set X, which maximize or minimize the objective function f of x in an n-dimensional space. In other words, X space the set of values that minimize f of x if the problem is maximization problem, minimize f of x if the problem is minimization problem. That means in computer optimization or standard optimization problems, the computer is optimized to undertake some functions, either to maximize the function or to minimize the function based on what the problem it's meant or the problem it's meant to be solved or how the problem is to be solved. So computer optimization is very important when using technology or computers in our various activities. So Let's look at some component of optimization problems. When analyzing optimization problems, we can identify four key terms. That means there are four main key terms that we will definitely identify when we are analyzing computer optimization problems. Objective function, decision variables, constraint, equality constraint, inequality constraint. So these are all key elements that we will identify when we ought to analyze computer optimization. This diagram here shows the steps involved in computer optimization, the roots of computer optimization, and the specific stages in computer optimization. We have the optimization itself, continuous and discrete. The discrete is made up of the IP, min-lib, and MILP. Differentiables, and the continuous is made up of the differentiable and non-differentiable. So all this comes together to form the process called computer optimization. Steps in optimization. There are various steps to be considered before we can optimize our computers, and these steps are identifying process variables and their characteristics, define the objective function, what to be optimized. That means in order for you to optimize your machine, you must know what you want to optimize, either the speed, the efficiency of the computer. So we must, or you must be able to identify or define the objective function. List all constraints. Check if the problem is solvable, and also choose an optimization method. Therefore, there are several optimization methods, so you must choose a specific optimization method based on the problem type, based on the problem you ought to solve. Apply optimization method to find the best solution. Interpret and act on the optimized results. So we move to winning modality. A winning modality function is one that has only one peak, maximum or value, minimum in a given interval. Thus, a function of one variable is said to be winning modal if given that two values of the variable are on the same side of the optimum. The one nearer the optimum gives the better functioning value. That means in optimization problems, there is a winning modal functions that correlate or that relate to things in the optimization of problems. So for example, a function f of x is winning modal if x2 is greater than x1 less than x, which implies that the function f or f of x2 is less than f of x1. So we move to convexity. The concept of convexity is very important in computer optimization. The concept convexity can be applied to functions or a space. A strictly convex function is one which can never be underestimated by linear interpolation between any 2 points on its surface. Similarly, a strictly concave function is one whose negative is strictly convex. So there are different types of convexity. You have the concave and the convex functions, which are mainly used or which which are considered in computer optimization. We have a linear function which is both convex and concave, but neither strictly convex nor concave. Here, we consider the purpose of a graph in optimization. As we have already seen, graphical representation of a function is a powerful tool in understanding the optimal values. So there are some functions we can only identify their optimal values based on or only on using graphs. This is useful for a function with one or two independent variables. So if you get a function with one or two independent variables, its graphical representation is the best for you to be able to identify the optimal values. We can also use plots to express optimality. However, the insight gained from single or two variable functions can be extended to higher dimensional functions. 3D plots of functions are usually done using surface or contour plots. So these are the main types of the graphs functions that are used when we are using the 3D plots. You ought to use either surface or the contour plots. So this is an example of the graphs we are talking about. The end to the need to appreciate numerous solutions techniques. In an ideal world, optimization problems would be seamless and straightforward with continuous, convex, and well-defined solutions. However, reality often presents us with a complex, non-convex, multimodal problems, replete with discontinuities and constraints. To tackle these challenges, optimization engineers must be well versed in a diverse range of techniques, including gradient-based methods, region eliminations, polynomial interpolations, problem transformation. So these are some of the techniques that must be considered or appreciated when dealing with numerous solutions in computer optimization. So we move on to modal formulation. A modal is a model is a informative representative of an object, an organ, or a system. It can also be defined as an abstract description of the real world, giving an approximate representation of more complex function of a physical system. That means a model is the art of representing a complex real or physical object by giving it a simplified form which will represent the complex object we are studying or the complex problem we want to solve. So a mathematical model involves a set of mathematical relationships, equations, inequalities, logical dependencies, which corresponds to relationship between the variables of study. So modeling allows us to avoid repetitive experimentation and measurements. Also, design phase involves providing the details of the model. So this is also a diagram which talks about an inequality and the concepts of entropy generations. We now move on to problem definition and formulation. This stage involves the conceptualization of the problem, which includes deciding the number of variables to be included in the model. So, not all the models don't have the same variables, and they come out with their own, maybe depending on the how complex the model is or how complex the real life problem is. Depending on the real life problems, you decide the number of variables to be included in your model, the number of equations to be included in the model, the number the number of unknown parameters, the level of details. Theoretical models. So we have theoretical models. These models consist of equations that are based on establishing engineering, science, and first principles. Well, conservative equations, phenomenological equations, and stuff are all theoretical models. So we move on to simulation and conceptualize and optimization. Simulation focuses on understanding and analyzing systems, while optimization focuses on improving system performance. To illustrate differences, consider a factory production line. That means in simulation might involve modeling the production line to analyze throughout bottlenecks and potential issues. So simulation and optimization has a common relationship. So we move on to types of optimization models. The following are some of the types of optimization models. We have linear programming, we have nonlinear programming, integer programming, mixed integer linear programming, mixed integer nonlinear programming. Introduction to classical optimization. The classical method of optimization are used in finding the optimum solution of continuous and differentiable functions. These methods are analytical and make use of techniques of differentiable calculus in calculating the optimum points. So calculus becomes one of the most important topic in terms of computer optimization or programming. However, most practical problems involves objective functions that are not continuous and or differentiable. The classical optimization techniques have limited scope in practical applications. So we are still on the classical optimization. So some common classical optimization techniques. There are several classical optimization techniques, but for this lesson we are going to consider the unconstrained optimization. That means finding the optimum and minimum function without any constraint. We have the constraint optimization, which is the opposite of the unconstrained optimization. We have linear programming, quadratic programming, Newton's method, gradient descent, and simplest method. We also have the Lagrange multipliers, which is a method for optimizing a function subjected to constraint by introducing additional variables. Thank you very much for this section. This ends the presentation. And again, it is presented by the group 35 of the PowerPoint project.